right? So this equation where rate of reaction is defined as dx upon dt, this cannot be applied to all types of reactors. This can be because if you remember, we have studied in chemical kinetics that this rate of reaction can be applied only when pressure and volume is not changing, right? So there is only one type of reaction, one type of reactor where volume doesn't get changed. It's your batch reactor. You know, it's this kind of a container tank, right, where reaction will take place. So here volume will remain same. So this equation is true only for batch reactors. This is not true for your continuous flow. When I talk about continuous flow, where the reactants is continuously flowing and your product is coming from the other way, from the other end. Because if you talk about continuous flow, right, what is happening is the concentration is not changing every day or every time, right? Here the change in here, if you talk about this in this tank, the reaction is taking place in this tank. So here the concentration of reactant, right, and concentration of product is changing. But here in this continuous flow, the concentration of reactant or product is not continuously changing. So this is not valid, right? This equation is not valid or is not correct. So we would not be dealing with this equation in our reactor designs, right? And remember that in chemical kinetics also we have studied that this is not applicable if this is applicable only if pressure and volume is not changing, which is true only in case of your batch reactors, right? So this is important to understand from chemical kinetics perspective also, and from our CRE, reaction engineering perspective also. And if you recall, if you remember this, that where this can be applied only when pressure and volume is not changing, it's easy to understand how it applies to reactors, batch reactor, or why we don't use it in case of reactors, right? So when we talk about reactors, right, the rate equation, what would be the rate equation? Because this rate equation is wrong, is not right for chemical reaction engineering. So the rate equation or the rate law that we used to write, right, in chemical kinetics, it's an algebraic equation that only depends on the function of the properties of reacting materials and reaction conditions, right? So the rate equation should depends only on the properties of reacting materials, that is reactants, and the reaction conditions. The reaction conditions, we mean the concentration, temperature, pressure, and the catalyst, like I stated above, the chemical kinetics, right? So this is important, right? So the chemical reaction rate law is an algebraic equation which involves only concentration, right? So the chemical reaction rate law, I'll just run it over here. Chemical reaction rate law, if you remember the rate law equations that we used to do in chemical kinetics, right, that the rate law, if you remember, as per law of mass action, the rate of reaction is directly proportional to the concentration of reactants, right? And that's the law of mass action. If you talk about rate law, that's the experimental actually, right? The rate law is experimental, like I just spoke before in this lecture. The rate law it's different from law of mass action, because law of mass action, if you recall, it was theoretical, right? Whereas the rate law was experimental, because experimentally the law of mass action, the rate given by law of mass action was not found true in many cases. So how actually the rate of reaction depends on the concentration of reactants, right? That gives you the rate law, right? And that rate law equation, right, that we are talking about here now is your experimental rate law, right? Not your law of mass action. If you remember, the law of mass action used to say that it's A, if I look at this equation, B, right? Whereas the experimental or the rate law was, this is as per law of mass action, right? And K alpha, B beta. This is your rate law, right? This is your theoretical and this is your experimental. This is your experimental. So here, what is the difference between these two? This rate law, the law of mass action is saying that you just have to look at the stoichiometric coefficients, right? Once you know the stoichiometric coefficient, you can write the law of mass action, rate of reaction as per law of mass action. Because if you remember, the concentration is raised to the power of stoichiometric coefficients, right? But here the concentration terms are raised to the power of alpha and beta, which may not be equal to A or B. So the rate law will experimentally tell you that how the rate of reaction depends on the concentration of A and the concentration of B, right? This gives you the actual rate law equation, right? This is an algebraic equation, right? So this is the correct equation, right? So if you remember, we have studied that the rate law equation, if it's given by R is equals to KCA, right? That means rate of reaction depends on the concentration of your reactant A, right? If you talk about, we have studied these kind of rate law equations also, Ca square, right? This is again how the rate of, if you look at this product, right? If this is the kind of reaction, it forms product D, right? So rate of reaction depends on these. This concentration is raised to the power of stoichiometric equation, right? So here rate law complies with the law of mass action, right? So these are the two kind of equations that you will generally see, right? So these we would be dealing with the rate law, which is based on the experimental conditions, right? So these are just looking more into little more depth for what we have already studied, right? So for a given reaction, the particular concentration dependence that the rate law follows, right, must be determined from experimental observations, right? Not from the theoretical. Theoretical is your law of mass action, right? So this equation is the rate of formation of, I can put it like A here, rate of formation of A, right, or rate of disappearance of A, right, to form, and I'm sorry, the rate of reaction depends on the concentration of A, and the negative sign is there because your A is, the concentration of A is going down, right? So here in this chemical engineering subject or book, you will hear the word rate of generation, right? You will hear the word throughout this book, rate of generation. Rate of generation is same as rate of formation that we used to use, right, in chemical kinetics. So I hope this is clear to you. Just remember, important things are, these are 5 pillars of chemical reaction engineering. A chemical engineer has always to deal with these 5 things, right? Here in this lecture we have discussed mole balance. We will derive in next video lecture mole balance equation, and mole balance equation is something that chemical reaction engineer has to deal with while working, right? It's very important. And we have studied about, in mole balance equation, what we are accounting for is what is going in the reactor, what is coming out of the reactor, and what is happening in the reactor, chemical reaction, right? And chemical reaction is, we will in inside this reactor we would be dealing more with chemical kinetics, right? What is the kinetics of the reaction, right? When we talk about kinetics of the reaction, we say that if you remember the definition of chemical kinetics, it tells the speed of reaction, factors on which the speed depends, and your reaction mechanism, right? So the factors on which the speed or the rate of reaction depends is your concentration, temperature, pressure, and catalyst, right? And we have dealt all these in detail in chemical kinetics, right? I'll put the links of chemical kinetics. I'll put the playlist there. If you have any doubts, you can watch those videos, right? And most important thing is the average rate, right, and the instantaneous rate, right? And the concentration of reactants changes with time. So we have made this plot. This is the curve, the tangent of this curve, or the slope of this curve, slope or the tangent of this curve will give you the rate of reaction, right? But we would be calculating the average rate of reaction. Why? Because rate of reaction falls down, because the reactant's concentration falls down, so the rate of reaction will also fall down, because rate of reaction is directly proportional to the concentration of reactants, right? So something is instantaneous rate of reaction, which is this equation, dx upon dt. Concentration of x is changing with time, and this is true only in case when the pressure or volume is not changing, right? So if we apply it to our reactors, it will only be true for this batch reactor where volume doesn't change. It doesn't apply to other reactors. Like in continuous flow, the concentration may not change even for a day or two, right? So it does not apply to your continuous flow or other reactors. In those reactors, we would be using this rate law equation, this algebraic equation, which depends on the concentration of, which is where the rate of reaction is directly proportional to the concentration of reactants. And these are the kind of equations you will get, right? And it should be experimental, not the theoretical, like that of law of mass action, right? So I hope all this is clear to you. Thanks.